Hi everyone, I am Mujahid Naseem from Hybrid Energy Systems and Optimization Laboratory, HERO Lab from Korea Institute of Energy Technology. In today's session, we will be discussing about the SOFC tutorial that is provided by the Ansys. This is actually, you can see this manual is a tutorial manual for the SOFC model. This was provided by Ansys, and this is actually for a tubular SOFC, and the accompanying manual is for calculating the fuel and oxygen utilization. This is all the files that are provided along with the tutorial. It has the PDF manual which you have opened and different contours, meshes, and especially the mesh. And for fuel utilization, there is another manual and the report definitions and the fuel utilization expressions. These two are the manuals that are provided by the Ansys. So the first is the tutorial manual itself, and the second is for calculating fuel and oxygen utilization. Proceeding with the tutorial, the first step is to make the simulation directory. In my case, I have made a directory and copied all the necessary files that are needed. For starting the tutorial, we will start by opening the Fluent. We should read this file in the case using with two solution processors and with double precision, and also show the mesh, because generally it is, you can see in the general options, display mesh after routing. So we check this option and go and start. So we have completed the first task, that is to import the mesh or read the mesh and display the mesh. So the next part is to check the scale. Check the mesh scales. And how to check the mesh scales? If you go to the scale manual in the top ribbon, and you can see everything is perfect. The lengths, they are accordingly 0.004 minus to plus, so everything is accordingly as required. This is normally good practice where once we make our own model. The next step is to display the mesh for different colors. So here we can actually go to colors and select by surface. So if we do by surface and display it, you can see that now we can see different coloring automatically for different surfaces, but we cannot see the inside. So what we should do is, for this purpose, to show the inside surfaces, we should go to view, options, outer face cullings. So here we can, if we check this option and apply, you can see the inside surfaces. So what it does is it removes the outside surfaces so that we can see the inside surfaces also. The model itself is there. So the next part is to create a ZZ surface, what it has called in the tutorial manual. So we will go to the domain and to the surface tab and create zone. So here it says to create a ZZ surface specified by fluid anode. So this fluid anode is actually a solid entity, and we will say it new surface name ZZ surface fluid anode and create it. You can check all the domains by going to the cell zone conditions, and here we have got two different entities, fluids and solids. They can expand these, and you can see we have 4 fluid regions and 2 solid regions. These are the current collectors, and these are the regions where there will be active transport, or the fluid will flow or diffuse. And the next important part is to define the electrolyte surface. It says to rename the wall electrolyte zone to wall electrolyte cathode. We can see the boundary conditions, and on the walls we can find what it says as wall electrolyte. Now this is wall electrolyte, and this is wall electrolyte inert shadow, and we will also have the shadow for this wall electrolyte shadow. We can display both of this because of this outer surface cullings. It's showing as a cut region. So for now we can go to options and apply, and you can see we are showing wall electrolyte and wall electrolyte inert, and this is actually the electrolyte surface, and the inert surface is the region that is not taking part. It's just for support, it's not taking part in the electrochemical reactions. So we don't, this is not of our interest, but the wall electrolyte is only the part of our interest. In order to rename it, double click it, and it is necessary to check what is the adjacent cell zone. Since the adjacent cell zone is fluid cathode, so we can rename it. It says it to wall electrolyte cathode, so that we can it will be, this will be needed later when we specify the regions corresponding to cathode and anode. We will do it shortly. Apply and close, and now we have got wall electrolyte cathode, and now similarly wall electrolyte shadow. So if I display this, you can see it is the same surface. It's a shadow surface corresponding to the different domain, and double click it. Now this corresponds to the shadow, this is the shadow space, but this is adjacent to the fluid anode domain, so we can rename it wall electrolyte anode. So wall electrolyte. So now we have two surfaces, wall electrolyte anode and wall electrolyte cathode. They are the shadow surfaces of each other, like this is the same surface but corresponding to different domains. If you go to the wall electrolyte anode, recheck it that it corresponds to the fluid anode side, and the wall electrolyte cathode actually corresponds to the fluid cathode side. Now the next step it is saying is to check and display the mesh. So we can go to the domain, mesh, and perform mesh check, and what it will give us the information of our mesh in the console. So we could go for display, mesh display. We display all inlets, outlets, and walls, and we can use it display. And like before, we will use outer wall cullings. Apply. After this, now we want to partition, because we specified two processors, so that means we can divide our partition. So it is a good time to define it, and it will be used later also. So go to the parallel settings and partition and load balancing. We can go to the partition and load balancing. Number of partitions will do only 2, and we should apply for Laplace smoothing. Cutoff aspect ratio 5 as what it defines in the tutorial manual. We're just following the tutorial manual. And okay, let's partition it. You see the 260 groups of partitioning including overlaps, merging, and okay, and use stored partitions. Close. Now we will start the actual solution. So for that we will go to models, but since there's no model of SOFC, we will add that later. So let's go to the models, and from models go to the energy. We want energy model to be on, energy equation, and this is not a viscous, this is a laminar, because the flow rate of the reactants and products is very slow. They fall into the category of laminar flow. So we'll select the laminar option, and now species we definitely need it on because there will be electrochemical reaction taking place, so we want to include the species transport. The reactions will be volumetric, full component diffusion, and thermal diffusion as well. Okay, so this is on, apply. Okay, and now we should add the SOFC add-on module. For that, click in the console, hit enter, and now it gives the commands that we can use. These are all the commands that we can go, and these commands are actually mentioned in the Fluent text user interface. This is the document that is available, Ansys Fluent text command list. This is available at the Ansys website also, and here if you go to the fuel cell module, fuel cell commands, this lists all the commands that are useful that will be useful in the fuel cells, for not just SOFC but all the fuel cell categories, including MFC, electrolysis module, and solid oxide with electrolyte as well. So these are the common commands that will be used. But right now we should go to define, because we want to define this module. Define, and if we enter again, you get the next set of commands that are applicable to define. And we want to go to models, so we can hit enter, models, hit enter again, and we have a number of models that we can go on to, but we want add-on, and now it gives a list of add-on modules that are available in the Fluent directory. Our currently we will be following the SOFC model with unresolved electrolyte. So hit the number 4, enter, and now it will initialize the SOFC module. And now you can see the SOFC module is available to us, so we can start it now. Enable SOFC module. The current under relaxation factor for this is a simpler geometry, since we are following the tutorial itself. Later we will want that the current under relaxation factor should be 0.2 for the initial run, and then we can increase it to 0.3. So right now we will be strictly following the tutorial manual and also the values given in the tutorial manual itself. So the total amperage, initially we would like that we always want to converge our we always like to converge our simulation to the very lowest, to the least system current, so that it gives us the OCV output. The electrochemistry, it has given the value of 1 exponent 12, 20 and 5 and 2. The rest of the things you can change it, but that depends upon your equations. This equations, for that the study for the manual of the Fluent theory guide, that is important to know the equations properly. And now in this side we select the wall electrolyte anode, wall electrolyte cathode, and tortuosity values and zones, tortuosity zones, and so these correspond to the zones or the domains that actually enable the diffusion. So we have got only 2 zones, anode and cathode, and the value is 3 for both. Apply. Now the next part is the electric field. So conducting zones. So what are the conducting zones? We select all. Obviously the current collectors are conducting, the channels are not conducting, and the cathode and anode are conducting zones. This is 1.5 exponent 7. Solid cathode side is 1.5 exponent 7. These are the current collectors. And now because there's material difference between the anode and cathode, they will have different values. For cathode it is 7937, and this is actually 333330. Now the contact surfaces and resistances. This is actually the contact resistance between the anode or cathode and the current collectors. So what it describes is 25. Now this is important to it has given a very important note that we apply this contact resistance to only one surface, wall cathode or its shadow. surface. These are both the same surfaces, so we apply the contact resistance to either of them, not both. And wall anode current collector, wall cathode current collector, and wall anode current collector. So these are the two surfaces that it has given. Here it is 1x minus 7, and for the cathode side it is 1x minus 8. Now this is very important, voltage tap and current tap. Voltage tap surface, it has during the meshing they defined these surfaces and apply. Okay, so this is defining the electrochemistry, and for this it is important to show respective from this model where these boundary conditions actually are. This is the anode of the SOFC, and if we display also the cathode, so the inside is the cathode and outside is the anode, and in between is the electrolyte that is sandwiched in between them. You see, the electrolyte that was inert is the portion that is contacting the cathode but not in contact with the anode, because the anode actually finishes over here. So this is actually the part that does not take part in the electrochemical reactions, and only the wall electrolyte anode, it will take part in the electrochemical reactions, as you can see right now. So, and displaying the cathode also. Now this is the cathode in between them. Now the main part is the current collectors. So if you go to the solid anode current collector and display it, it is on the top. Now one very important thing is to get the voltage tap surface. See, at the top of the anode, this is the surface that is actually generating the voltage. Now the current collector is, if you go to the current collector and display it, so this is the current collector. This surface is the current collector. We have got the anode, the cathode, voltage tap, and the current collector. The next part is checking the function hooks and user defined scalars. If you go to the user defined and function hooks, it just says to check if these are done. Normally it is automatically done. Scalars, all zones, and user defined memory. We have got 14 memory locations. The next part is to define the materials, and then we will apply them onto the cell zone conditions. The first to define the materials. For that we go to the solid material and go to anode default. The anode default material, we are not applying the anode default material, we are just giving it into the library, adding it into the library. So defining here will not tell if this is the anode. We can give any name over here. So this is anode default solid, and we give the values that are given in the manual. And thermal conductivity 6.2. Create change, close. We defined the anode default material and now the cathode default material. Now for the thermal conductivity, it is constant at 1.15, but it says to give a piecewise linear function. It defines to give a piecewise linear function. Now here we give piecewise linear and two temperature points, 0.1 at a temperature of 5 and giving it a value of 570. Now next point, point number 2, and with a value of 565. Okay, so now we got the piecewise linear function to change. Now for the next, we can have anode collector default. Now these are the current collectors. Anode collector default, it gives to give this the values 8900, the same we will go to cathode collector default and give the same values. Now we have defined the material, and it mentions that the SOFC mixture only accounts for H2O2, water and nitrogen. In case of CO electrochemistry is disabled, then the relevant species of CO and CO2 need to be added into the mixture by the user. And right now we define the materials, and now we need to apply them to the zones. So first we go to the fluid zone, anode zone. Go to fluid anode. First thing is porous zone. So viscous resistance, inverse of absolute permeability. Either we define the permeability or the resistance. So it defines to give this value the resistance of 10 exponent 13. Earlier we defined the material as a solid material, and now we should give the porosity. The porosity of this is 0.3 for the anode, and this here we define it as the fluid anode default material. Now we are actually applying the previously defined material that could have been any name, and now we apply that the fluid anode, the zone name fluid anode, is made up of this material. And we go to apply, close. Likewise fluid cathode, it is having SOFC mixture. The fluid that will flow into it is SOFC mixture. Going to the porous zones, again one will give the same. Porosity is 0.3. Material is made of cathode default. Apply. Now we need to define the current collectors. For the current collectors, there is no porosity or other things. Solid anode current collector, and this is made up of anode collector default. That's it. Now we will go on to the boundary conditions. For the boundary conditions, we give it to the inlet. Go to the inlet anode, right click it and type mass flow inlet. It's already defined as mass flow inlet. Okay, so the 2.49 exponent minus 7 is the value that we have to give. Now thermal block, it enters at a temperature of 973 Kelvin. And species, now this is at the anode, so it has hydrogen and water. So the hydrogen is 0.48 and this is 0.52. Now this should be remembered that this is in mass fraction. So if we give it in mole fraction, it will convert into mole fraction, so it is actually 90, almost 90% in terms of molar ratios, but in mass fraction it is like this. So define the thermal and the momentum, apply. Likewise, now for the cathode, we can give it, this is also mass flow rate, 0.37 exponent minus 5 kilograms per second. Thermal, this also enters at 973 Kelvin, and the species is O2 mainly and 0.23. Now we need to define the outlets. So the outlet, it tells normally that we should define the outlet in a way that there's no backflow. So for defining the outlet at the anode, the temperature, because the reaction will take place and the temperature is bound to increase. So from 973, an estimated is at the anode side, it has given 1250 Kelvin, and species that are, this is not the exact species that will give from the simulation, this is a guess, it can be any value, but sure there should be logical values, that's all. And mass fraction of 0.2, and going on to the solution methods, this is both ways it's possible, from the ribbon or from the tree. Now it tells to give the controlling limits for the maximum absolute pressure, 5 exponent 10. Okay, this is already default setting, so we can keep it like that for our case, and this is also okay. From the default settings are all are upwind conditions, so that's also okay. Simple scheme, that's also okay. In this session we will just import the equations and the report definitions. In the next session we will discuss on how to apply them ourselves. So now is a good time to save it, because from here we will start the next session also. So this is a good time to save it, file, and we will write case into our Gblue sample. Let's give it step 1. Okay, now we have saved the file, and now we can move on and save it afterwards. We'll save it again. Now we can actually import the report definitions and the name expressions. So the report definitions, right click it and import from file. The expressions it has given, the report definitions, cell report definitions. Okay, and you can see there are a lot many invalid. It is not defined, the fuel utilization, since the expressions are not defined. So, and you can see these are invalid right now, but after importing the expressions, now we can set import from file expressions. Now we have got a few expressions also. You can see we have got expressions for mole fractions, fuel utilization, and report definitions also. So, go on to monitors, and now we can actually get report plots. You can add new. So the first report plot is H2 and O2 utilization. H2, O2, percentage, and we want to select it fuel utilization mole fraction and auto utilization. The plot title should be H2 auto utilization. And we printed every iteration. Okay. Now next is the min and minimum maximum temperature, and here we want to get all the temperatures. The minimum and maximum temperatures at anode and cathode. To check if there is no local starvation for hydrogen or oxygen, we give the minimum mole fraction available in the anode and cathode. Minimum mole fractions that are at the anode and cathode. And report plot. Okay. Now this is most important: cell currents and voltage. Cell current, currents on taps. Currents on taps, cell current on voltage tap. Ideally it should be the same because the same current flows through the cell. And cell current voltage tap and cell current tap. The last is the cell voltage. Okay. Now we are ready to initialize the solution and run the solution for the first time. From the ribbon, go to standard initialization and initialize. So the next step is to give the cell about 50 iterations and run it. So we will try to make the same graph that it has given in the tutorial manual. So for the first time we'll give 50 iterations and start the calculation. You can see all the scaled residuals, it's converged properly, very good convergence is achieved, and the fuel utilization right now is very low because you gave the very small amount of current. The next part, this is almost zero current, so if you go to this even at 50 iteration is 0.067 at this will be a slight difference between the anode and cathode because there's not going outside the circuit, so there will be a small difference between them. And we can check the exact value of the currents if you go to the report definition and go to the cell current values. Cell current tab and compute it. So we get this total current that has been generated, although we gave it 0.01. This is on the cell current. This is the current tab. Now if you go to the voltage tab and compute it, now you see at the voltage tab we get the correct amount of voltage that we required. So this is the voltage tab current that we should get. And now the voltage, if we want to compute the exact voltage, go to cell voltage and compute. This is about 1 point, and this is the OCV voltage we are getting. And this is important to check that we have selected cell. Here it mentions that for fixed voltage boundary conditions, the cathode value will be larger than the anode value. So if we go to the anode side, we want to compute the cell voltage, and we try to get it at not at the current tab, and we try compute the at the voltage tab, compute, get 0. Voltage tab is the reference, anode is the reference, and to get the maximum voltage we have to go to the current tab side. Current tab and compute. This is the actual voltage, the OCV voltage that we are getting. This is the actual output. But for the current, now the current will be in reverse of it. It's not from the current tab, but it's from the voltage tab actually. Okay, now the actual voltage that we specified initially in the model, that was, if you go to the model and go to the, we specified a total of 0.01 amps and 0.01 amps will be achieved if you go to the cell current tab. This is not giving the correct value, this is giving a very high value. And we go to the cell voltage tab, and here if we compute, we get the correct voltage that we desired, that the desired current. Now following the tutorial, now we should give different voltages, so we will follow it and we will give it different, converge at different specific voltage. And now this simulation already converged to the OCV. Now we can give 1.0 volt, apply, and give it 100 iterations and calculate. As now we applied a higher load because we decreased the decrease the voltage. Now the current will increase in the response of decreased voltage, and for that the power or the consumption will also increase. So the H2 and O2 utilization actually increase, fuel utilization increasing quite much, and O2 utilization increases also, but the temperature also increases from the OCV to the 1 volt, and you can see the minimum local fractions for hydrogen that has increased significantly. The current on taps exactly increased, the current increased, but we see the sudden drop in voltage. Now we will keep decreasing the voltage every 0.1 till 0.4 as given in the manual. So now 0.9 volt and calculate. Okay, now we continue, keep moving forward. 0.8. okay, and calculate. Now we will move towards 0.7 volt. Okay, we have finished the calculation till 0.7 volt, but at this point we would like to see the graphical plots. And for graphical plots, because 0.7 volt is the generally operating voltage for many SOFC systems, so we will like to see the graphical solutions or the contour plots at this instant. So if we go and import from file, so we can import the contours, and you can see different contours. You see, right now we should disable the outer wall culling, and you see the mole fraction of nitrogen, mole fraction of oxygen is abundantly available throughout. But if you go to the now, hydrogen is being consumed, and initially it is abundant at the inlet, but it is being consumed as we move along the length of the fuel cell. As the reaction goes on, the temperature also increases. You can see that, and the voltage generated throughout at the this is mainly the electric potential at the electrolyte surface. Activation over potential. So you can see all these graphics by importing them. You can also import the scenes. So these are the we can also have the velocity vectors of mass fraction of O2. According to the mass fraction of O2, we can have a look at the vector plots. Also from the cathode side, it is entering, right? The blue region shows that there is no oxygen present at these locations. Obviously at the anode side there is no oxygen, but likewise we can also have the current density vectors. That is the most important. This is the important part, that we should have the current density. So if you go close up, this is the current density vectors plots. So now we continue the simulation for decreasing voltages up to 0.4. And solution, calculate. And as we are applying more and more load, the temperature is also increasing. But these fluctuations are because the fuel utilization and the local starvation of the fuel cell is occurring. And you can see the minimum mole fraction, that's going up to 0. There is no fuel present. So in the graphical units, we go to the mole fractions of hydrogen, and display it, so we see that most areas doesn't not are not equally having the hydrogen available, so these areas are starved. So we need to increase the fuel supply, and this is the next part of the tutorial. So the first part of the tutorial, the first set of solutions that we have done is the corresponding to the in the from the tutorial manual figure 24. This is the till this point we have got the same results as figure 24, and this is the OCV voltage 1. This is the conversions for 1 volt, 0 0.9, 0 0.8, 0 0.7, 0 0.6, 0.5 and 0.4. So now we can get the polarization curve by getting, for example, if you go to the H2 and O2 utilization, we can get the fuel utilization, the value, take as end as possible. So at this volt, this is the OCV, 1 volt, 0 0.9, 0 0.8, 0 0.7, 0 0.6, 0.5 and 0.4, and we'll try to take the last value over here, or any value. It's difficult to get any value over here because of the fluctuations. So an estimate is okay, we got an estimate of 98.2018 and somewhere here 29.8, but here the values are pretty stable, so we can take any value corresponding to these and tabulate them. So we will find that these values corresponds to the table, or to this is, yeah, and then we can plot the polarization curve, IV curve. We have the voltages and the current on taps. Now the current on taps are also almost similar. There's no big difference between voltage tap and current tap. So this can also, we can see at the report definitions. If you go to the report definitions, and at any instant, because of higher load cell at current tap, we compute the voltage 10.39, and at the voltage tap 10.34. There's no big difference between them, so we can use either of them, but since we start with the voltage tap current, so we'll stick to this one, and we can plot the IV curve. Now is a good time to save as our step 2, so we'll write the case and data and call it step 2. Okay, we will start. For the next step, we will start by increasing the fuel supply with applying more and more load, and we will increase the fuel supply accordingly. This corresponds to table 3 in the tutorial manual. This concludes the first part of the tutorial. What we have seen that the residuals, they become very unstable and started to diverge. This is because the hydrogen, if you see the fuel utilization, that was not complete. The 100% fuel utilization was there, so there was insufficient supply of hydrogen or fuel. So as the next step, we will introduce more flow rate of the fuel to the anode side, and to do that, we will do the second set of analysis. So we'll initialize it again. We will initialize it again, and by initializing, all the results that we have got, they will disappear. Now we will set up again, and this first condition is again at a current of 0.01. So we will go back and resolve it at a current of 0.01 ampere. Okay, and we will again run it for 50 iterations. Calculate. Since we initialize, now the scale residual start from 0 iteration, and likewise the hydrogen and oxygen utilization, where initially they are at 0, the temperatures, they are minimal, and everything as at the initial stage. Now instead of just increasing the load, we will also increase the fuel supply. For that, first we'll go back to the SOFC model, and here we will give the 1 volt, and manually also change the boundary condition for the inlet flow rate. And as specified in the tutorial file, we will increase the inlet momentum. So the initially we will give it 1.8 exponent minus 8. Apply. So, and we will give it 100 calculation. So we have done the first set of analysis, and you can see the convergence is going very well. The current increased slightly. The voltage we gave it again from the same 1.067 volts to 1 volt, and current increase, and likewise the temperatures will also increase because we have applied the load, so there will be more electrochemical reaction going on. Now as the next step, we'll again increase the load by 0.9 volt and also increase the fuel flow rate. 1.25 exponent minus 7 kilograms per second. Apply and run again for 100. This concludes the third step. We have solved the third step, and the convergence is going well, and the hydrogen and oxygen utilization, you can see because of this jump we are not able to monitor, but see that the fuel utilization is also very good, and it's still in not up to going as high as previously. So now again we will apply more load from 0.9 to 0.8 volt, and the inlet fuel flow rate from 1.25 to 2.59. Solve again. Now you can see there's a big jump in the temperatures as well. We have increased the load, so there's a big jump in the temperature as well, and this temperature is going to keep increasing as more load we apply. The temperature will keep increasing. So now we'll increase the load by applying 0.7 volts and also increase the inlet fuel flow rate from 2.59 to 4x. Calculate again. Okay, now as the next step we will increase the load further 0.6 volts and increase the fuel supply also. So this calculation is also completed, and now as the next step we will move on by applying more load 0.5 volts by applying the load, and we will increase the mass flow rate by to 1 exponent minus 6. Calculate. So this is the load when we have applied 0.5 volts. Uh, Moving forward, before moving further, we would like to take some pictures, because as mentioned, as given in the tutorial, the figures given for the temperatures, nearness potential, they are all corresponds to 0.5 volts. So at this point, before moving to 0.4 volts, we'll take a look at some figures. So if you go to the figures, so the first figure we have is the temperature distribution on anode and cathode. So we can go towards the temperature and display it. So this is the temperature, the static temperature on the, this is only the anode side, but you see there we have got a lot high temperature. So this is one point to mention, that as we keep applying the load, it's not like we can have we can extract as much power as you want. It's limited to the temperature, and this causes very high temperature gradients will cause structural problems, so the temperature is limited. The next the next figure that we want to show is the electrolyte surface, the temperature on the electrolyte surface. So we have the temperature in display, and again we have got the temperature distribution on the electrolyte surface. Now we have interface current density also. We can save it, the interface current density in ampere per meter square. Nernst potential. You can also draw the mesh like given in there. You can draw the mesh and display, but transparency we can have up to 90%. Display, no edges, partitions, close. So you can see within inside, if we you see within the cell, now we can it gives a much better picture. And for the Nernst potential also, we can give it, instead of exponential we can give it float, so you can see the voltages. Voltage in volts at cathode and the cathode side. So here it's a good time to take all the pictures also. So you can take the pictures from the safe picture tool, and from the safe picture tool you can get JPEG image or PNG. I prefer JPEG, and from JPEG you use 100% Windows resolution with white background, and if you preview it, see you get a picture like this, a much better picture, very beautiful picture that can be put directly into the manuscripts. And we can have save it, save as step 2, or you can give any name for electric volts, and especially do mention at what voltage or what load condition you are in taking this. For example, you can name the picture as electric potential at 0.5 volts. So 0.5 volts, this is important. So because you will have the pictures at figures at different load steps, 0.5 volt, zero point 0.6, zero point 0.7, so it is important to mention the load step. So I will cancel it right now, and will move on to, you can have all the figures and control plots. Very important is that you can also have the vector plots for the current density. The vector plots, it gives the amount of, it gives the electric potential flow in the cell. Now we will move further towards the 0.54 volts. So for applying the 0.4 volt, now as mentioned in the tutorial, this will not be solved and it will show some convergence problem. So we will give 0.4, and at the same boundary condition of the inlet fuel flow rate, we will give the same fuel flow rate and solve it. Now we'll go to the scaled residuals, and we will see that we will have some convergence problems. Okay, now you can see the from the scaled residuals that we are getting significant issues for the convergence, but the main problem is the oxygen utilization. Most of the oxygen is utilized, so the fuel cell is actually getting local starvation, and the temperaturize, they are getting insane values of temperatures. So if you go to the minimum mole fraction of oxygen at the electrolyte surfaces, you will see that it's nearly zero. So there's no oxygen present. And why is there no oxygen present? This is also mentioned in the tutorial file, that at the highest load applied, even the nitrogen present within the cathode, it prevents from oxygen to move towards the electrolyte, because oxygen is being consumed, so it's continuous being depleted, but nitrogen remains the same. So the mole fraction of nitrogen remains, the total amount of nitrogen remains the same, but oxygen is depleted. This accelerates, this causes hindrances for the oxygen to reach the electrolyte. So what to do, how can we see if this is the real solution, this is our if this intuition is correct? So at the end of the tutorial, what they do is, at the same voltage, now we will just increase the mass fraction of the oxygen, to justify a hypothesis that is the oxygen if the oxygen is not adequate at the electrolyte surface, now we will increase the flow rate, not just flow rate, only the species concentration of oxygen, because nitrogen is providing hindrance for the oxygen to reach the electrolyte surface. And now if we increase it, right now it's 0.23, and now we increase it 0.345 and apply, and now again solve it. The solution is complete. And now you see when we increase the oxygen mass fraction, the oxygen concentration in the inlet coming air, which is not possible. This is just to support our hypothesis that oxygen was prevented from nitrogen. So you see it started to converge, and even the output power, if you see the currents, it increased. This is also if you see the minimum local mole fraction, and the mole fraction of oxygen is significantly increased. It's not zero, it's there. So now if we increase the mass fraction of the oxygen to 0.46 and solve again, now you see, now we have solved it, and from the minimum mole fraction you see that the mole fraction have increased significantly from of oxygen, and the fuel is being more utilized. So the minimum mole fraction of oxygen has decreased, but the temperatures is steadily increased because it was generating more power, and likewise the current on taps it also increased. So this demonstration concludes our the SOFC tutorial. In the next session, we will continue by giving our own report definitions and the named expressions. Bye and see you next time.